Did you know that a dirty ship hull can increase fuel consumption by up to 40% and spread invasive species across our oceans? And it's not just ships. Offshore wind turbines, aquaculture cages, underwater sensors all face the same costly challenge: marine biofouling. In our latest episode, we dive deep into the cutting-edge solution designed to fight it. From smart biocide-free coating and biomimetic surface inspired by shark skin, to proactive cleaning robots and even electric surfaces. Discover how scientists and industry are reinventing antifouling technologies to protect marine structure, cut emission, and keep ecosystem healthy. I speak with Professor Christine Bressy, director of the MAPIEM Laboratory in Toulon. She is the perfect example on how our research lab can drive real-world innovation for a more sustainable ocean industry. Listen now on BlueTech Around the World. Welcome back to BlueTech Around the World, the podcast where we explore the cutting edge of ocean innovation and blue technologies shaping the future of our seas. Today we are diving into a topic that sits at the crossroads of chemistry, engineering, and environmental science, the world of antifouling technologies. For those less familiar, biofouling is the unwanted accumulation of marine organisms like algae and mollusks on underwater surfaces, whether it's a ship hull, an offshore platform, or even aquaculture cages. It's a natural process, but it comes with a heavy price: increased fuel consumption, higher greenhouse gas emission, and rising operational costs. In fact, the International Maritime Organization, IMO, defines antifouling paints as coating applied to underwater surfaces to prevent marine life from attaching, improving efficiency, and reducing environmental impact. But here is a catch. Some of these paints, and especially those using biocides like tributyltin TBT in the past, have also had severe side effects on marine ecosystem, persisting in the water and entering the food chain. That's why the IMO adopted the International Convention on Control of Harmful Antifouling System on ships, aiming to ban toxic substances like TBT globally and push the industry towards safer solutions. So today, antifouling innovation is at the heart of many hot topics: sustainable coating chemistry, biocidal versus non-biocidal coating, AI data-driven performance assessment. And to help us unpack these complex topics, I'm thrilled to welcome a true expert in antifouling innovation, Professor Christine Bressy. Christine has over 20 years of experience in developing marine antifouling coating. After earning her PhD in polymer chemistry, she dedicated her career to understanding how coatings interact with marine environment, not just at the lab bench, but in real-world conditions, through field tests, bioassays, and collaboration with industry. Today, she leads the MAPIEM Laboratory in Toulon, France, where she and her team work on sustainable antifouling strategy, bridging the gap between science and industrial application. So Christine, welcome to BlueTech Around the World. I'm so excited to explore this topic with you.
Thank you, Marilu, for this kind invitation to talk about antifouling strategies and more specifically sustainable strategies.
My entire pleasure, Christine. So Christine, I would love to start with the basics, because while biofouling is a huge topic in the maritime world, not everyone outside the industry knows what it really means or why it matters so much. I already gave a small definition in the intro, but can you explain what biofouling is and why antifouling technologies are crucial for our maritime industry?
Okay, thank you. So marine biofouling is defined as the accumulation of marine organisms, as you previously said, so bacteria, algae, mollusk, on any surface immersed in seawater. But when we go in deep consideration. First, when you immerse a surface in water, quickly you will find some marine bacteria which settle on the surface rapidly. I mean, rapidly in few hours. They grow and develop some biofilms. And these biofilms, with time, mix complex microbiological communities. And these biofilms are dominated by bacteria diatoms. And then, with time, a more complex communities of multicellular colonizers grow on the surface. And after 1 week, 2 weeks, you are able to see by yourself some macroorganisms like algae, tube worms, and also mollusks, so mussels, but also barnacles. So there are several macroorganisms. Some are classified as soft falling, like algae, they can move. And also the others are defined as hard fallers. And these fallers are very strong with calcareous walls. And it is worth noting that there are more than 4,000 falling species in the oceans and seas with different mechanisms of adhesion on the surface. And so their density, their diversity are dependent on geographical and seasonal variations, and also depending on the depth of immersion, but also depending on the type of surface. So the shape, the chemistry of the surface also is also important parameters in the colonization process. So the massive diversity of species makes difficult to tackle marine biofouling. So this is a great challenge for researchers and industry to find antifouling strategies that target the widest range of marine species. So why antifouling technologies are crucial for marine industries? As you previously said in the intro, marine biofouling causes serious issues in marine industry and transportation. First, ship hulls, propellers, blades, pipelines, offshore platforms, aquaculture equipments, and also sensors, among others, are affected by marine biofouling. And also when we talk about maritime or marine transportation, we need also to look at and consider sea chests. Sea chests play also an important role because in the sea chests, you can accumulate biofouling and release biofouling in the marine environment. And so this is also the main cause of the introduction and the spreading of the variety of taxa, what we call invasive species or alien species. And so commercial vessels are really the main, I would say, actors in transportation of this kind of alien species. So you know that the IMO and other international organizations and also regional collaborations have recognized that biofouling from ship hulls and ballast waters plays a role in introducing invasive species to a new environment. This is really a bad issue, and New Zealand, for example, has recently made mandatory that all vessels arriving in their waters have to clean hull to prevent the introduction of unwanted organisms. Also bad issues for aquaculture equipments because biofouling on fish nets and cages led to substantial economic loss to manage it. Also for sensors, monitoring sensors when you want to collect oceanographic parameters or physicochemical parameters for water quality assessment, such as temperature, salinity, turbidity, oxygen, or chlorophyll A, the equipment are subjected to biofouling, which decreases their long-term quality of measurements. So this is also an impact. And this is why we need to protect surfaces against marine biofouling. And so the technology could be different depending on the biodiversity. So the type, the water, the temperature of the water, the geographical location, and so on.
Thank you very much, Christine. And just listening to you, we really understand that it's a complex topic. As you are mentioning, that there is a huge diversity, depending of the localization, depending of the depth, depending of the area. So a lot of diversity, and I think a lot of different solutions to manage this biofilm. And as you mentioned, it's a natural process beginning from microorganisms with biofilm and escalating to macrofouling with like mussels and barnacles. And I like the way you really show the impact both in terms of economics, like the fuel consumption, or for example, the aquaculture industry, but also an environmental aspect with the introduction of invasive species, for example. We talk a lot about the ballast, and there's a lot of regulation regarding the ballast treatment before entering a new port, a new area, but I didn't know about the story of New Zealand for the cleaning of the boats before entering their water. So that's really, really interesting. So now I'm curious. We talk about the problem and why is it so important. So I'm curious about the common methods currently used in antifouling and how they have evolved over the years.
Yes. So currently on the market, we have two main strategies. The two main strategies are focused on the use of paints. So paints we need to apply by spraying paints on the ship hulls to protect for maritime industry. And when you want to protect the hull, it's easier to apply a paint. And there is two main families of paints. Paints containing biocides, also called biocidal antifouling paints, and also paints without biocides, so biocides-free. And the difference between these two main technologies rely on, first, for biocidal paints, it's the release of biocides from the paint or from the coating with time in contact with water. And so the concentration of biocides released drives the efficiency of the coating. So you need to control the release rate of the biocides. And the second technology, it's biocide-free. The mechanism of action is different. You need a coating which is quite soft, and you need to have some surface properties to be able to inhibit the adhesion first, or even if the macroorganism or microorganism could settle, you need to release them easily. And so you need the hydrodynamic force. And so when the boat or the ship is moving, the organism can be released. And we call this coating the fall or fouling release coatings. In that case, the technology is focused on silicone elastomers. This is something we can use in your bathroom. When you put an adhesive all around to protect from mushrooms or organisms, and you can clean it easily by using a sponge. So you remove all the bacteria and so on. So this is the same process. It's more or less the same chemistry. You limit the adhesion because it's silicone, like silicone mold you can use. And even if some organisms like the silicone, because it's a chemistry and some organisms like silicones, that they can settle, but you can remove them because the interaction forces are very weak. So this is a second technology.
So really the one using biocides, like a paint that you will put on the ship, and the other one more working on hydrodynamic and other materials to first avoid microorganisms to attach. And if they still are there because they love silicon, for example, with the hydrodynamics, the ship moving, this will help for the release of that. So thank you for this clear explanation. From your perspective, how do they choose between these two different technology?
So biocidal paints, you talk about the TBT paints. So this is a quite old technology. TBT was banned by IMO, and paint manufacturers developed other paints containing other type of biocides, excepting TBT-based product. And so this is quite old technology, but they replaced TBT by copper-based biocides, for example. They use a lot of copper oxide. They added a lot of copper oxide in paints with levels or amounts higher than, I would say, 50% of the paints containing copper oxide. And they add some booster biocides to be able to obtain a wide spectrum of activity against all the different kind of organisms or micro and macro. So this type of paints, up to now, it represents around 90% of the market and applied on chip holes. And then you have the silicone-based technology, so the fouling release coatings. I think the first patent was applied in 1977, so it's quite old technology too. But as soon as TBT was banned, then research and development focused more on fouling release coatings. But the efficiency of the fouling release coatings, you need that the ship is moving. So when the ship is, I would say, in the harbor, in stationary state, is not good at all. The coating is not efficient at all. So that's why the biocidal coatings are effective in static and in dynamic conditions. But fouling release coatings, the previous generation of coatings, were efficient when the ship moves at a speed around 20 knots. Then with time, they increase the performances of fouling release coatings. And now you can find some fouling release coatings or paints efficient even at 5 knots of speed. So this is a real evolution of the performance of fouling release coatings with time. And that means that, probably in the near future, the balance of the percentage of biocidal paints and fouling release paints will change. But it's not so easy to change the market and to change just because their fouling release coatings have also some drawbacks. And that's the reason why it takes time to change the mentality and to go further on this kind of biocides-free coatings.
Okay, thank you very much. It's interesting to see how the market evolves regarding the adoption of this new technology. And I know that I think it's IMO that state that biofouling can increase a ship's fuel consumption by up to 40%, depending on the extent, of course, and type of biofouling. So that also contributes significantly to higher GHG emissions and operational costs. I can see this shift, and it's good also that they can adapt to lower speed, because we know that IMO now is pushing for lower speed, for, of course, the emission, also the underwater noise, which is also another topic that is quite interesting. So I can see the shift in marine transportation, but regarding static offshore elements, such as offshore wind, for example, or aquaculture cages, is there any innovation or technology on this side, or we are still on the biocide painting?
Yes, for static infrastructure, it's really complicated. It's a tricky problem because without any biocides, fouling release coatings don't work. So what we can do, we can combine fouling release coatings with, for example, a cleaning process and trying to find the best frequency to clean the surface, and using what we call grooming procedure. I mean that you need to combine technologies for static infrastructure. And from my point of view, the best combination could be fouling release coatings because it's easy to clean, and you combine these coatings with a cleaning process, so in water cleaning process, using robots, for example. But you need to do that as a proactive procedure. not a curative one. So you need to do it frequently to be able to remove easily the microfouling. If it's too late, then you will have some macroorganisms and you will spend energy and money to remove remove them. And then also you can damage the coating and you can create some debris, which could also have an impact on the environment, because we can say in that case that you generate microplastics during the cleaning process. If you want to detach some mussels or barnacles, it's very difficult to detach them. So you can also remove coatings during the cleaning process. It's not good at all.
Actually, I love your view of that sometimes there is not the perfect ideal technologies that answer all the challenges, but sometimes we need to combine different techniques, different approaches. But the most important, as you were saying, is to be proactive and not reactive, because of the way we could have a lot of damage on the environment. Um, Talking about this subject, as I know you have good relation with the industry, even if you are in the research and science side, when you talk with industrials, do you see this shift with proactive, with this innovative mindset? You were talking about underwater robots also to do the cleaning.
Yes, yeah, there is a shift. There is a shift because, as we discussed previously, it's very difficult to develop a technology which is efficient against all kind of marine organisms and all kind of I would say condition of navigations. So you need to combine technology, and as you need also to decrease your impact on the environment. We talk about also maritime decarbonation, as you mentioned. They have to think about all that parameters. And so there is a shift. I would say owners, well, people who owns vessels look at combining technologies and also in water cleaning robots. But what is difficult today is to define clearly the protocols you need to use, because the protocols of cleaning is really also depending on the coating you have applied on your hull. In that case, you have to take care that the result could be worse by combining the two technologies. So you need to know exactly how coatings works, what is the mechanism of action. And as soon as you understand the mechanisms, you are able to fine tune the conditions for the cleaning process or procedures. And at that time, there are different way of cleaning. And so you can adapt the cleaning procedure to the coating or the technology of the coating you use.
Thank you very much. You know, most of the time when I speak with the industry to step forward regarding environmental issues and protection, most of the time at the beginning there is an economical insight. For example, the cost of fueling in the maritime transportation, or regulation, for example, IMO. But I can see also that some are more and more green and try to reduce their impact on the environment. So it's, I think, the combination of different factors on that. I would like to come back on so the environmental impact of the traditional tiefling techniques. Is there any like the impacts on, I will call that non-target species? Because in the intro you said there are a lot of different organisms depending of the area. So how do you manage to say this one I don't want to use, this one it's okay? How do you manage this kind of question?
Okay, so I will talk about in Europe first, because in Europe there is the biocidal product regulation. So there is a list of biocides which are authorized to be on the market and which could be formulated in paints. So there are not a lot of products. available on the market to be used in antifouling coatings regarding the biocides. So you're right. All the biocides or the molecules, we can talk about active molecules. Biocides mean that you kill organisms, but you can only be active without killing. So I will say active molecules. The molecules could be active against targeted organisms. And when we want to avoid the adhesion of algae, we use a biocide which is specific to algae. But this is a molecule, a chemical molecule. So this molecule could be also active or could be toxic towards non-targeted species. And in that case, we talk about ecotoxicity. And when you look at all the reports you can find regarding product regulation, you can find some data on the concentration or the effective concentration or lethal concentration of this kind of molecules towards specific organisms of different we call trophic levels. Biocides could be active against targeted, but should not be toxic against non-targeted species. In Europe, there are some regulations, but also in other countries regarding the use of this kind of biocides. But what is also important, it's the concentration released in water, because the ecotoxicity depends on the concentrations. So if you are able to control the concentration released in seawater, you can be active without being ecotoxic against non-targeted organisms.
Thank you, Christine, for this clear explanation and making the distinction between the two. So now can we discuss some of the latest innovation in antifouling technology? I know at MAPIEM you have been working on smart polymers, vibratory systems. What are the new topics? I know that there is even biomimetic surfaces. So can you share more about this, what you're doing at MAPIEM, the laboratory in Toulon?
Yes, I can share some advances in developing antifouling strategies. What we want when we go through the development of more environmentally friendly technologies, biocides-free now, because at the beginning we just focused on decreasing the amount of biocides compared to commercially available paints on the market. So we tend to decrease the amount of biocides. Now we go through the development of biocides-free technology. So we focused at that time on fouling release coatings without biocides, trying to enhance the performance in static conditions, as we know that fouling release coatings are not so efficient in static conditions. So we develop amphiphilic coatings. That means that your surface of the coatings exhibit hydrophobic and hydrophilic domains. And we know that some organisms prefer hydrophilic or hydrophobic. And we define a surface which is called an ambiguous surface. That means that the organisms, if you put several domains of different chemistry, the organisms, when it comes and touches the surface, the organisms say, well, this surface, it's a good surface, so I'm going to colonize it. But when you touch very close to the first position, you say, oh no, I don't like this surface. And so he really doesn't know where he is. So what kind of surface? It's ambiguous surfaces. And then by this way, we can limit or inhibit the adhesion or the settlement. So that we decrease the colonization. In the meantime, we tend to also look at, as you talk about, biomimetic surfaces. So trying to develop surfaces with a microstructure or microtextures close to the shark skin, for example, because also we know that there are not a lot of marine organisms and also like muscles on the skin of a shark. So if you look at the microscopic, I would say, scale, you can see some microstructures. And so we tend to develop some surfaces like that, try to mimic the nature. But it's quite difficult to upscale this technology because the process you need to use to develop this kind of micro texture, it's quite expensive. And because you need to use, I would say, laser ablation, 3D printed. So it's completely different from a paint you apply by spraying. So it's completely different. But you can try to use this technology on films and stick a film on the ship hulls. This could be a way also to replace paint. And also we focus on surfaces which are active by generating electricity, for example, currents, electricity. And the marine bacteria doesn't like electricity. So there are a high variety of technology you can use. But the main point is to combine them. If you don't combine the different technologies, you won't be able to develop efficient technology, I would say efficient in any kind of conditions.
I can see that there is not like one best solution to follow the market. As you mentioned at the beginning, you were trying more to reduce the impact of biocide solution, and now you are more focused on finding biocide-free solution. But as you mentioned, some of them are really expensive. We also need some scalability if we want a broader adoption by the industry. So there is always this balance between the efficiency, the impact, and also the economical aspect for as a broader adoption for the industry. I would love to come back a little more about biomimicry, looking to nature for inspiration. You talk about the shark. I know that there were some idea about the seaweed, the coral mucus too, and about all this thing of developing some microstructure surface. How do you explore all the solution regarding biocide-free solution?
Oh, yes. We collaborate a lot with foreign researchers, but also in France. We have some colleagues also in Little Brittany, and they are working also on this kind of topic, but quite few in France. So we collaborate with different countries and also different institutes because, as you mentioned, we need to develop new strategy, but you need to test them and you need to develop also some platform of testing. And it's also not easy because in that case, it's more focused on engineering. It's not chemistry, but you need to develop some tests which could be representative to the real life. And so we need to collaborate. So it could be more fundamental research, but also more applied research. And also with companies. They are also going through developing coatings or strategy with less impact on the environment. And so they also need some, I would say, background coming from academics because even if some of our research are more fundamentals ones, we tend to understand why and how we can manage the biofouling. And so we can also have collaboration to develop paints with small companies also, focusing also with, I would say, water-based paint, because probably you know that the paints we use contain solvents and organic solvents. And so we also in the past developed water-based paint with small companies. We need to collaborate also with industries because we need also to have all the factors, as you mentioned, there with the efficiency, but there also the toxicity or impact on the environment, but also the economic part. And so if we want to upscale a technology, we need also to collaborate with industries.
I'm curious if in these sectors, is there already some startup or technology provider who wanted to answer these challenges, or is it still in the research and academia area?
No, it's not. It's not only in academia. It's there is a lot of, I would say, startups which want to develop or put on the market a new technology, because you already heard about other kind of technologies I didn't talk about earlier, but you have the use of ultrasounds, the use of UVC, also the use of air bubbles, for example. I would say we heard about different additional technologies, but you need to combine these technologies with coating. So you can't use them alone. So there are a lot of startup working on that, trying to find new strategies. We had a lot of contacts, a lot of discussions on technology they would like to develop. And so our background, because we worked on that topics for many, many years now, we can also say that this technology could be, I would say, efficient, but also the efficiency is the first step. But also most of the time you need that your technology you develop, it's cost effective, but it's effective regarding the antifouling, the impact on the environment. So you need to consider all, but for sure, it's an open subject. As we said, it's difficult to tackle marine biofouling. So the legislation also helped to reconsider everything and to start again with new technologies.
Good to know that everyone is at the table, the industry, the new startups, technology provider, but also the research centers, academia, and as you just mentioned, the policy and the legislators to give the framework and to push forward better solution and less impact in the environment. And one topic you just said about testing the efficiency and also the cost. And most of the time, it's true, we are really focused on engineers and not too much on biology or chemistry. So I think it's really important to have this taste phase where we can try and collaborate and make some tests to evaluate some of the solution. I think it's really, really important. And as you mentioned, international collaboration and cross-sectorial and transdisciplinary approach is really important for that. And actually, on this specific subject, is there already some like testing protocols or certification to improve the market adoption regarding anti-fouling solution?
Yes, there are some standards for static or dynamic immersion. These standards could be French standards or American standards or ISO standards. But depending on the technology you use, you need to develop new protocols, new tests. For biocidal paints, we have standards. For fouling release coatings, we don't have. And for new technologies, also we don't have anything. If we use other technologies like cleaning or UVC or ultrasounds, there are no protocols. So you need to develop protocols of tests to be sure that your technology is efficient and the efficiency time of your technology. If it's a new coating, most of the coating are classified depending on the efficiency time. There are, I would say, sub-families, and you need to know if your new technology will last 1 year, 2 years, 3 years, 5 years, over 5 years, and to test them. As it is a new technology, you can use standards, but some of the standards are not reliable to your technology, so you need to define new ones. So
Okay, thank you very much. One question, because we talk a lot about the digitalization of the maritime industry, digital transformation. Is it something also that apply in these sectors?
oh yes, for sure. There are. It's quite surprising when you come from academia or when you talk with paint manufacturers. And if you want to select one coating or one paint on the market, when you discuss with the paint manufacturers, it's unbelievable. They are able to, depending on what you want, where the ship will navigate, the frequency of navigations, and so on. They have some software because they have already implemented ships and they know exactly what kind of coatings you need. So that means that for sure in anti-fouling purposes, when you put some sensors and so on, and the digitalization of it's very important. It's very important to optimize the technology you will use as a coating, depending on the navigation route and conditions and so on. And this is quite well impressive also to see that all could be monitored, and the paint manufacturers could propose you the best, I would say, or the best performing technology depending on your condition of navigation. So it's amazing.
Wow, looks really inspiring. And actually, yeah, all the data to have the historic with depending of
Yes.
the road, the ship, the area, to such as a decision support tool to make the best suggestion
Well,
of the coating that is better adapted to your specific case. So great to see that digitalization is also there helping for anti-fouling solution. Now I will like more to give your expert view. You already gave us some insight on the new technology. What do you think will be the next step, the next innovation, the next trends regarding the anti-fouling technologies in the next decades?
well, I think that we go through the development of biocides-free technology for sure. Biocides-free, but also silicone-free. Because now we tend to hear that fouling release coatings containing silicone elastomers could release also some silicone oils or surfactant in the sea, and they are not assimilated by the marine environment. So you could have a bioaccumulations in the sediments and so on. So silicone free, it's the next generation. That means that we need to find a new solution as efficient as the one already on the market, the ones already on the market. I don't know if you know, but in the paint you have some biocides, but you have also polymers, which is a matrix which is from the film, the coating made of polymer macromolecules. And I think the next generation will more focus on biopolymers. So polymers are synthesized by, for example, marine organisms like bacteria. We know that some polyesters could be synthesized by marine bacteria. So use this polymer synthesized by marine bacteria to do a coating. Also, it would be interesting that this biopolymer is also biodegradable. And there are already academia and industry working on that kind of new polymer matrix to develop coatings from nature, so marine organisms or others, extraction of I would say biosource polymers. And also these polymers should be biodegradable, because when it releases or in contact with marine environment, and to avoid accumulation, also the polymer matrix should be biodegradable. So this is the upcoming innovations.
Wow, thank you, Christine, for this insight. You know, I work in different sectors of the blue economy, so not only marine transportation. I'm coming back to the, I would say, static, for example, aquaculture cages, offshore wind farm, where biofouling is growing challenges. But also, you know, there is all this communication about the artificial reef and the ecosystem advantage and impact of this offshore infrastructure. Does this other industry are as mature as the marine transportation industry regarding the research, the investment regarding a new technology on this subject?
They are looking at what is already done in shipping industry, and try to, I would say, take the best of the technologies or the less toxic technology and the lower impact on the environment. So we can use technology already developed for shipping industry to marine renewable, I would say systems in general. It's it's not so far. Even if it's static conditions, then that means that you need to combine technology. And as I talk about the grooming or the cleaning process, it's not so easy to clean and to go and clean, I would say, marine renewable equipments. But you have to think how you can remove mechanically also the fouling. But they are thinking about, they are looking at what is already done in shipping industry. It's not so easy also to transfer the technology to the shipping industry, to other maritime sectors like aquaculture also, because in aquaculture you have fishes also. So but they are looking at, and I think combination of technologies also, it's something we should be considered for other kind of, I would say, application areas of in static conditions, for sure.
I think that this will be the key takeaway message, that it's a combination of the different strategies and innovations that will make things works and have the less negative impact on the environment, and also have this cross-sectorial dynamics between the different sectors of the blue economy. Thank you. Just one last question regarding the work you are doing with MAPIEM. You talk about the different innovation, new technologies that are coming in the market according to you in the next decade. What are the most promising projects that you are actually working on right now at MAPIEM?
Wow. It's not so easy to answer because we have so many ideas to tackle marine biofouling. I would say trying to find the best solution over the world. And say that MAPIEM, it could be then a leader in the anti-fouling strategies. We try to develop the best performing system. So we go further and further, and it's really a really exciting scientific sector of research. So many parameters to drive and to control, and so I would say that there are so many. So I'm not able to answer only one technology. Sorry for that.
No, no, actually, you are saying that this need a transdisciplinarity approach, and you are doing your best to be the leader of the sector.
Yeah.
So actually, I'm really proud to be from Toulon, the south of France, and knowing that there is MAPIEM who is targeting this kind of issues. Christine, thank you very much for this conversation about antifouling technologies. It's clear that behind these technical topics lie major environmental and economic stakes, from reducing emission to improving operational efficiency, and has the objective of the decarbonation of the maritime industry. So before we wrap up, is there any final message you'd like to share, maybe for the next generation of scientists, engineers, or innovators who might not realize how critical and exciting this field is, and how to embark them in the blue economy and blue technology worlds?
I would say that there are places to do a lot of things, still innovating in these topics. It's really, I would say, a sector, an application area where innovation will last over a year because of the regulation and so on. So if new researcher or new student wants to go further and trying to developing the most performing technology, well, it's really a big family, but also a small family, and with really exciting, I would say, issues at the end. So yeah, feel free to join us.
Good. That's a message. And I know the new generation, we, I include myself, are really targeting a job that makes sense with an impact. And the fact, as you mentioned, that there is a long-term vision, potential for innovation. That's good. So for any students or youths that listen to us right now, come to the blue economy and work on the future of anti-fouling solution. And to our listener, if you find this episode insightful, please subscribe and leave us a review. It might seem like a small action, but it really helps us keep bringing you more stories about the technology shaping our ocean. And so until next time, stay curious and keep exploring. Thank you very much, Christine, for being here with us today.
Thank you, Marilu.